Hi everyone. So I realize this isn't quite an ideal setup and I apologize for that, but it's the best that I got. So we're going to solve the ballistics problem. So in this situation we have a 10-gram bullet. Alright, so I'm going to write down that we know the mass of our bullet, I'll call that with the lowercase b, is going to be equal to 10 grams, which we want to convert to kilograms. So let's see, that'd be 1, 2, 3, so 0.01 kilograms. All right, we have a 10-gram bullet fired into a 1 kilogram wood block. So I'll call that mass with a capital B for our block is 1 kilogram. And this bullet lodges into the block. Subsequently, the block slides 4 meters across the floor, and then they gave us a coefficient of kinetic friction of 0.2. So mu k is 0.2. We know the distance we travel, so I'll call that just d, is 4 meters. You want to know what was the bullet's speed. So that's the speed at which the bullet enters the block. So you want to find velocity of our bullet. All right. So this problem here is going to be basically a two-part problem. All right, so if we want to diagram our situation, so initially what we have going on is our bullet, and it's fired with this velocity we're looking for into our stationary wood block. So initially our wood block is at rest, and we have our bullet moving towards our wood block. Then we have the situation. So our interaction here is the bullet and the wood block. When the bullet lodges into the wood block. So now we have the situation when the bullet is in our wood block, but before this system starts moving across the floor. So we've got some sort of velocity here that we'll sublabel a little bit, but we want to find what this velocity is, as we'll see in a minute. And then we have a situation in which this system here, so our block and our bullet, are moving across the floor. All right, so here this travels to a new position over here with the bullet in it, and we know that's 4 meters. And so the speed here of the system is now at rest. So I'll label this with the F for final. Maybe I should label that as a 2. 1, 2, 3. Nah, for now we'll leave it as final. Oh, sorry. I said we knew that was 0. So that's 0. We don't know what this, I'm going to call this right now, initial velocity is. Right? But we know it comes to rest after 4 meters. And then we want to find the velocity of the bullet before it even goes into our wood block. So in order to find this, so what we should identify is that we're going to use momentum conservation to solve this system here. So in order to find this velocity, we're going to need to find what this velocity is. And we have to use momentum conservation when it comes to this interaction of the bullet lodging into our wood block, because this is an inelastic collision, so energy is not conserved. If energy is not conserved, we have to use momentum conservation. So dealing with this interaction, we're using a momentum conservation. But that means we need to find this velocity here, the velocity of our mass and bullet initially before it starts moving that 4 meters. Now, in order to find that, we're actually going to use energy conservation of this situation of when it's traveling the 4 meters. We're not going to use momentum conservation because that's not going to help us. So, but energy is conserved in this situation. Well, it's not conserved. The work energy theorem holds. So let's actually start with looking at that. So we know that, actually I'll start working over here. We know that our work is equal to our change in energy. Here in this situation, the only work we have going on is the work due to friction, and this is assuming that we're putting the objects in our system are the block, the bullet, and the earth. Right? If those objects in our system, then this work is going to be the force of friction times the displacement times the cosine of the angle in between that force vector and that displacement vector is equal to our change in energy, where our change in energy here, we know we have a speed here, we know we don't have a speed here, so we're going to have a change in kinetic energy. In terms of potential energy, we are actually moving along the same height, so our height doesn't change, so we don't have to worry about gravitational potential energy, and we don't have any springs, so no spring potential energy. So our only change in energy is going to be our change in kinetic energy, and that's going to be equal to the work done by friction. So the angle between our frictional force and our displacement, we're displacing to the right, so that means our frictional force is acting to the left. So the cosine here is the cosine of 180 degrees, which is equal to -1. So we have negative force of friction. Force of friction, if you remember, is going to be mu times our normal force. Our normal force of this object here is going to be equal to the weight of this object because it's not accelerating in this up or down direction. Right? So the weight of this object is going to be, so actually let's write that here. So we know our normal force is going to be equal to the force due to gravity here. So mu times our force due to gravity times our displacement, or our distance here, negative, is equal to our change in kinetic energy, which is 1/2 mass times our change in velocity squared. Force of gravity we said was equal to the weight, so that's negative mu times, now be careful here, the mass is the mass of the block plus bullet. All right, so it's going to be mass bullet plus mass block times g, right, because we know the force due to gravity is m times g, multiplied by the distance we travel is 1/2 m, and I was sloppy here. I didn't specify what this mass was. This mass here is the mass of our object we're analyzing, which is the mass plus bullet. So this here should actually be, I'm just going to write that right now as total mass, but that is also our mass of the bullet plus the mass of the block times our change in velocity squared. So what's nice here, our masses cancel. Now when it comes to our change in velocity, our final velocity, so this is our final velocity squared minus our initial velocity squared. And we said this final velocity here was 0. So if we simplify, we get a negative mu gd is equal to 1/2 our change in initial velocity squared, and we don't want to forget that negative sign. So our negative signs here are going to cancel. Now remember, we're solving for this velocity because we want to find for right now, the speed of which it's when it starts moving moving those 4 meters. So if we solve for this, we get 2 mu g d is equal to our initial velocity squared. So then our initial velocity here is the square root of this quantity. But we're not done with the problem, right? So now we know that this velocity here is that expression. We could calculate that out, but I do not have my calculator on me, so I'm not going to do that. Let's see, sorry, I'm having trouble seeing here because I'm literally wearing my tripod around my neck. So, lots of fun. 2 mu g d. All right. So looking back at our situation here, now we want to find, so our goal in the problem is to solve for the initial velocity of the bullet. So now we know, so now instead of saying initial velocity here, we can call this now our final velocity. So now we're analyzing our situation, dealing with change in momentum, or dealing with momentum conservation. Because you know the total momentum before our collision is going to be equal to the total momentum after. And now we have that final speed. Let's grab a new sheet of paper here. Ooh, nice and spotted. Let's flip that over. Okay. So if we want to deal with momentum conservation, we know the total momentum before, so our initial momentum, is going to be equal to our total final momentum. Initially, we have two objects, the bullet and the block. So this is going to be the initial momentum of our bullet plus the initial momentum of our block is equal to our final momentum after our objects are now combined. So that's going to be, I'm just going to call that our final momentum, and we'll subdivide it into a little bit. So momentum is mass times velocity. So we have the mass of the bullet times the initial velocity of the bullet, which is what we're solving for, plus the mass of the block times the initial velocity of the block, which we know is 0. This block is initially at rest. This whole term goes to 0. And that's equal to our final momentum, where our final momentum is the mass of the block plus the mass of the bullet, because these objects are now embedded one within the other, times its velocity, which this here is our square root of 2 mu g d. Now all we have to do is some rearranging. All right, so if we're solving for this, all we have to do now is divide both sides by the mass of the bullet. So the initial velocity of the bullet is equal to, we're going to have the mass of the block plus the mass of the bullet divided by the mass of the bullet multiplied by the square root of 2 mu g d. And that's basically it. Now we just plug and chug. All right, so we're plugging in the mass of the block, which we said was 1 kilogram, the mass of the bullet in these two spots, which we said was 0.01 kilogram, multiplied by the square root of 2 times mu, which is 0.2, g, which is 10 meters per second squared, and multiplied by our distance of 4 meters. And like I mentioned, I do not have my calculator here. Earlier when I did this calculation, hopefully when I plugged in all the correct numbers, I think I got a value of 404 meters per second, but I highly recommend you check my math on that. All right, thank you.